not all of you were on the first part, so just a brief introduction. I'm dealing with data mining and SQL Server for 30 years, wrote 13 books and coming to 10 courses and more. I'm focusing mostly on these topics like data mining, statistics, advanced data modeling, data quality. So in the second part, I'm going to describe estimation algorithms, linear regression and regression tree. One more kind of a predictive or classification algorithm support vector machines. Time series, different clustering algorithms, association rules and sequence clustering. So a lot of work to do, but I assume that either you visited the part 1 or are already familiar with definition of data mining, so I'm skipping the introduction, which took me like 1/3 of presentation in the first part, so we can focus directly on algorithms. So remember, the focus is on algorithms. I will show demos in analysis services, in Excel and in R, but the focus is on algorithms, not on tools. So the idea is to explain how these algorithms work, how they get data, the results from the data, and so on. So let's start with estimation algorithms, and those who visited the first part remember the main difference, or the difference between predictive and estimation algorithms, is that you predictive or classification algorithms work on a discrete target variable. Now we have a continuous target variable. And of course, if you want to express one continuous target variable as a function of another continuous variable, it means you need at least two continuous variables. Otherwise, linear regression makes no sense. It will return you the result in the form of a constant. So y equals a constant. So in linear regression, we want to show one variable as a linear function of another, like y equals a plus b multiplied by x. So in multiple linear regression, we have more than one independent variable or multidimensional feature vector that consists of these multiple independent variables. So y equals a plus b1 multiplied by x1 plus b2 multiplied by x2 and so on. So let's start with one dependent and one independent variable. So these two variables form a two-dimensional plane, and the values define coordinates of the points in this plane. Now if you draw these points in a scatter plot, with linear regression you are searching for a line that best fits all of the points. So this is what you are searching for. So how do you define the best fit? So the points must be all together the closest to the line. So this is best fit. So you measure the deviations from the line, the difference between the actual value for some point from the line value, okay? From the line value. You want to minimize these deviations. Now you cannot just sum them, because some points will be above the line and some points will be below the line. And if you use simple sum, then this will not give you any information, because most of these values will annihilate each other, so the sum will be 0. So you will not find the best fit line. So how do you overcome this? You square the deviations, so you are measuring squared deviations, right? And then you can calculate the slope of the line and the intercept of the line with the y-axis. So the slope, you calculate deviations from each point to the mean of this line, y, and multiply by deviation of x in this point from the mean of x, divided by the sum of x minus, in this point, minus mean of the independent variable squared. So intercept is then calculated with help of slope, is the mean value of y minus slope of y multiplied by the mean value of x. And this is the formula. So how does it look graphically? So you have these points in a two-dimensional plane, and what you try to do, you search for the line that minimizes these squares of these deviations. Now this is very simple, and then you use this line with linear interpolation, you predict new values. Okay? So you simply extend this line and predict new values. Now this might be oversimplified model for many business cases. So this is also a global model. So we have a single line that covers all data points. Now not all or most of business relationships are not that simple. So if you remember, neural networks and even logistic regression try to do some nonlinear transformation. Now with these nonlinear transformations, we have another problem that is hard to understand the results. So regression trees go to a different direction. So we have trees, so it will be something similar to a decision tree. So we subdivide this working space, this area where we define this multiple linear regression formula. So we divide these points in subsets. And then we calculate multiple linear regression formula for each subset separately. So we got piecemeal multiple linear regression formula. So how do you define these partitions? Well, you can use discrete input variables for this division. And then you can continue to divide these partitions more and more until again some stopping condition. And this is of course completely, the first part is completely the decision trees algorithm. And once you have all of the nodes you need, then you can calculate multiple linear regression formula in each node separately. So you got piecemeal regression formula. And regression trees can be even smarter. Now, imagine that you don't have any discrete input variable, but you have multiple continuous ones. Regression trees can be smarter. You can define these splitting points also in the points of nonlinearity of these continuous variables. Imagine that you have some variable that goes like in sinus. So in every peak or valley, you define a cutting point, splitting point, and then you use this variable as a discrete one for splitting the tree. And the rest ones that do not have any points of nonlinearity are used for regressors, for multiple linear regression formula in these nodes. So, remember from the first module, or first part of this data mining algorithms, we said that logistic regression is basically a very simple neural network with no hidden layers. Similarly, we can define linear regression is a very simple regression tree with no splits. One formula for the global data set, and you get linear regression. So regression trees, I have similar points as with linear regression, just that I split this based on some input variable into subsets, and then I calculate the multiple linear regression formula for all of the subsets. Now I can estimate this target variable on new data, use discrete variables to define the subset, and then use the formula for the subset to estimate the outcome of the continuous variable, right? Like family income for a credit applicant. So, as I said, in order to get something meaningful, we need at least two continuous variables, one predictable and one input. Linear regression is extremely simple to understand, maybe even overused algorithm for all kind of forecasts. Definitely overused because, you know, we are prone as human beings, as people, we are prone to use it because we live in linear time. Time changes linearly, so we understand linearity very well, but non-linear functions, we don't understand them They are not built in, in us, so we don't really comprehend them. So we tend to simplify problems to linear problems. And then, of course, you make big mistakes if a problem is not linear. Regression trees might be much more accurate in many cases, because even if the actual functional dependency is non-linear, like something like this, if you get this piecemeal regression tree, you can kind of follow the curve very, very nicely, and still is easy to understand. So it might be very, very useful. Linear regression is also useful, but as I said, maybe even abused and overused for many cases where a more complex algorithm would be more appropriate. So let me go to my Visual Studio and let me define a new named query in my data source view. Remember that for the first part I used only discrete variables. So now I will create a new named query which will add age and yearly income to continuous variables to my data. So let's call it target or just TM regression. So I will use this for regression, copy the query and define the key. So what I got now is I got a couple of continuous and couple of discrete variables. So I have to create new mining structure because I'm not sharing the same structure. I'm having different variables. And you see, there is no regression trees algorithm. Actually, regression trees is hidden in decision trees. It's there, so I will use decision trees, and I will feed decision trees also with continuous, predictable and input variables. So TM regression is my case table. Now let me define inputs and predictable. So I will use this one, let's say like yearly income, okay? And then I will use also, I will pretend number of cars owned is something between 0 and 4. I will pretend that this is also a continuous, so I will have multiple linear regression formula. And definite, no, this is input, and definitely age is input. And I can use all of others, even bike buyer, commute distance as inputs. I didn't define which one is continuous yet. Let's see here. The wizard properly found that age is continuous, bike buyer is not, it has only values 0 and 1, so it is discrete. I will leave number of cars owned as continuous, although it has only 5 different states, and yearly income. So I have 3 continuous variables: yearly income, number of cars owned, and age. I will not use the testing, although I could use similar testing, not leaf chart, it's not so simple, but you can still test the values, okay, and measure the total deviation. So I will say TM regression, let's call it TM regression trees. Finish. And let's see how these things are used. So I will check with properties. So modeling flag, regressor. So you see, this was done automatically by the wizard. Bike buyer, I said, is discrete, so it can't be a regressor. And number of cars owned is also a regressor. So this modeling flag regressor means use it for linear regression formula. Even it has points of non-linearity, don't use it for split. Because I have only 3 continuous variables, I will leave it as this. If I would have multiple continuous variables, I want to have multiple linear regression formula, that's the point. In a real project, I would remove this flag, so I would leave to the algorithm to decide whether it's better to use this variable for split or for regressor. It has a lot of heuristics inside,
So it can be easily used, so it's better to leave to the algorithm to use variables as it wishes. So I will create on the same structure a new model, linear regression. Like this. So I will use linear regression and I get immediately a warning. You see, linear regression doesn't do any splits, so it simply doesn't support any discrete variables. But I can still share the same structure. I will just click yes, and what happens here is it will simply ignore most of the input columns. That's it. So let me now deploy this project and process it. And of course, processing, especially regression trees, could be again quite long, because remember, we have to go all through the decision trees process and then calculate the regression formula. And now let's see the results in mining model viewers. So this is the regression tree. And you see, I have, let me enlarge this first. I have a different presentation in these nodes, different from decision trees. In decision trees, we had distribution of the target variable in a line. Here, we have a continuous target variable. So this tells me, but it's still pretty negative. This tells me the mean value, and this tells me the deviation of this variable in class all. And if I go to mining legend, what I got here is this multiple linear regression formula. So this is overall multiple linear regression formula. Just try to remember some of the numbers. So yearly income equals 57,309 and so on, plus 12,000 and something multiplied by number of cars owned minus this, plus 170 multiplied by age. So this is the overall formula. Why should we remember this one? Remember that linear regression didn't do any split, so it should be the same as the linear regression formula, the overall one. And now we can see what was used. No, what is I don't want to see the splits. This is just the idea, so I can follow the splits here and I can see the legend. So if occupation is professional and number of children at home equals 1 and total children equals 2, I have 542 cases, and the multiple linear regression formula in this node is different. Okay. Dependency network, similar to decision trees. So what has the most influence? Of course, occupation, the number of cars owned, number of children at home, and so on. Right. Age, which is also a regressor, doesn't have so much influence as some of the discrete variables. So you see, regression trees gives you a lot of information. Now if I go to linear regression, I have the same viewers, just here is no split done. I have only the all level, and all of cases are here, and you see the same formula as in all level of the regression trees. So same two viewers, also dependency network, just with only two columns, and number of cars owned is more important than age. Okay, of course it's logical. It really depends. I mean, I don't have very good variables, so I decided for this two for continuous. So basically, linear regression is similarly as logistic regression, included only for the sake of simplicity. You could always fake them through either in regression trees not using any discrete variables, or how would you fake, if you remember the previous model, how would you fake logistic regression with a neural network. You just go to the neural network and set algorithm parameters, and one of the parameters is hidden node ratio, which is calculated with some formula that uses this hidden node ratio as a multiplicator. So if I simply put hidden node ratio 0 here, I will get a logistic regression. Okay. Support vector machines. Support vector machines is in a way more similar to predictive algorithms, decision trees, and naive-Bayes than this estimation. But it's much more complex. Mathematics behind is much more complex. I will not go into details, but you will be able to imagine immediately where the complexity comes from. So it's used for classification, but also for regression. So also in advanced support vector machines, target variable could be also continuous. So it fits in both modules. So let's say that we are talking about discrete target variable. So similarly like other classification algorithms, support vector machines training algorithm builds a model that assigns a new example into one of the categories of the target variable. So support vector machine is representation again of cases as points in multidimensional space. Multidimensional means that input variables, the number of input variables defines the dimensionality. And then support vector machines try to separate, to create categories in these cases, so in such way that the gap between two groups is as wide as possible. Wow, what does it mean? Imagine that I have only one input and one target variable. So I would use similar approach as with linear regression, right? To find the line, just this time not the line that fits the best all of the data, but the line that splits the best all of the data. And if I use more input variables, like I have three-dimensional space, then I'm searching for a plane. And in n-dimensional space, I'm searching for a hyperplane that splits the data. So if I have binary target variable, I'm searching for one hyperplane. If I have multiple states, I'm searching for n-1 hyperplanes. So now you can imagine why the mathematics is pretty intensive and complex. Imagine it's like calculating multiple linear regression on nth degree, right? But the idea is similar. So we have these hyperplanes or set of hyperplanes, and then we use them for classification. So new case comes to this subspace of the full multidimensional space. And then we can read what these hyperplanes mean. So instead of finding, if we go to 2 dimensions, instead of finding the line which has the lowest deviations from the points, we are searching for something different. Line that splits the data in such a way that the deviations are the highest. So imagine I have support vector machines. This would be kind of linear regression. This would be the line that fits data the best. This is not what I'm searching for. First of all, it doesn't even split the data. Some data is on the line. Data shouldn't be on the line if this should be used as a splitter. So I'm trying with a different approach. This is already something nice, but I can do it even better with line like this. The distances between points to the line are higher than with this example. So this would be my two subsets of my full data space. So you can imagine that this is pretty complex calculation. So I'm not even writing the formula, but basically formula doesn't look much different from the formula for calculating the slope and the slope of the multiple linear regression. Just you have a lot of sums in front. Sums over, sums over, sums over, this and this and this. So become very complex. So how do we use support vector machines? They are powerful for some specific classifications. First of all, they are not so good in predicting human behavior, like we predicted in previous presentation, the outcome for bike buyer target variable, what leads people to buy a bike. This is not something that would be nice with support vector machines. Support vector machines are not good in fraud detection. The mathematics is simply too complex. You see, sometimes the bigger complexity doesn't give you better results in some cases. We don't use so complex mathematics intuitively. So our decisions are simpler. And I don't want to underestimate anybody, but this is how we work. Our decisions are not so complex. However, support vector machines can do a lot of good job in these classifications for machine learning. So support vector machines is more machine learning than data mining algorithm, more machine oriented. So learning about images, classifying text, character recognition. Here is where support vector machines can give you great results, better than other algorithms that are more human oriented. So let me show you an example, and now I'm limited to R. Support vector machines are not even supported in analysis services, which is more human oriented. So, but the algorithm is very intensive, so again I am creating a small subset, first limiting number of rows, then limiting number of columns, and then defining a data set from this, and now build the model. R, is very nice, but as I said, this is not so good for production. Even with 18,000 cases, I would have problem of building this model. It doesn't do, in this free version, doesn't do parallel processing, etc. So now I can get a summary of this, how many support vectors were created. So this is basic information. So a lot of subsets of data was created. So it's really kind of hard to understand. Now I can make the predictions. And let me show you a table with these predictions. So I have only a couple of cases. So this is the actual value of Y, which is bike buyer, and this is the predicted value. And you can see now this depends on the implementation. This implementation hasn't built normalization in it, but lower values represent zeros and higher values represent ones, right? So you can see, you can get some connection between predictions and actual values. As I said, this is not really human oriented. Now the problem here is also that although I used only 200 cases, I at least could train the data, but still I am not able to plot this data. It's still too much for this built-in graphics. So I will use another data set that comes with R, right? So I have another data set that comes with R. I have iris data set about iris flowers, and we have 3 different species of iris flowers, and we have data for petal width and petal length and sepal width and sepal length. And based on this, we can use support vector machines to try to predict species. I'm using this data set just to limit the number of variables so I can get some meaningful results for plotting. So now I'm creating a second model, and this model can be even plotted. So these are actual, this is actual data from this algorithm. These are data points, and you see that I have only 40 points, not really big data set. And these different colors are different species, and this shows you the separation lines in 2 dimensions. Let me go back to the plot. So I'm showing petal width and petal length in dependency of petal length, and just for specific sepal width and sepal lengths. So it's really hard to interpret this algorithm. As I said, it's useful more for machine learning than for data mining. But with this slice, I can see this split into 3 groups. It was pretty well done, so I have most of these black cases in the blue group and most of green in the violet and in red cases in between in the white sector. And as I said, because this is not in analysis services, I cannot even use support vector machines in Excel. Now, what if you need this for more cases? Then, fortunately, it exists in Azure ML. And of course, you can use R algorithm, but it's not scalable enough. So in Azure ML, Microsoft added own algorithm that is scalable. Okay. If you would really like to use support vector machines. But as I said, this is more useful for machine learning than for people predictions. Decision trees give much better result here. Now let's go to the forecast. So what is the problem with forecasts? Well, forecasting is the same thing as predicting, just it's about the future. And this is the problem. Right? Forecasting the past is simple, or forecasting the current state is simple. At least you can check the prediction immediately. How forecasting the future, this is more complex. First of all, it is a very specific data preparation. It's always a lot of work with data preparation, but for time series, it's even more specific. First decision is, you see, this is a very, very nice example where more data gives you worse results. It's not just about the processing time. It's simply don't use too much data. Why? How much history do you want to include? Imagine that you are forecasting sales of a mobile phone model. If you will use 15 years of history, then your forecast would be, I don't know, Nokia 6310, the best seller for next year. So probably you don't want to do this. Also, by the way, you know why is forecasting also so complex? You always forecast based on experience, so you cannot forecast something that you don't have experience with. Very nice example is you can be completely sure that Coca-Cola knows everything about Pepsi-Cola and vice versa. However, they both overlooked Red Bull. A new player with a new product, all right, and showed the market and everything, and nobody could forecast this. If you, and you know, then the question is it possible to forecast this? Well, can you do this for me? Can we hire you to do this mining model for me? You know, if I would know how this in advance, I wouldn't sell just a mining model. I would sell Red Bull. It's so simple. So the answer is no. Oh, sorry. Oh. Based on previous evidence, in this was impossible. Some things are possible. Some things are, maybe you noticed that even with decision trees, I had 2 states of target variable, or with naive was seen very well. And I had 4 columns for frequencies of input variables. One was for population, one for state 0, one for state 1. And there was the 4th column, which was added for imaginary 3rd state missing, which was not missing. So this way we can add imaginary states in some algorithms and then also get predictions for things that didn't happen yet. It makes sense. Makes sense. Again, think of real life. If you would use history of American presidents, you could never forecast that Obama would become a president. If you would use only data from the history. All presidents were white males. So also Hillary Clinton doesn't have any chance if you don't introduce an unknown state. I mean, she's got known state, but in the model you need to introduce an unknown state.
right? So if you aggregate or categorize input data, then you might use more history because patterns in broader groups do not change so frequently. So maybe like mobile phones, you can categorize in, I don't know, smart and dumb or cheap, expensive. And then you can use more history. Also, you need to understand what are parts of the time series, and depends on your task, you maybe want to get rid of some of these parts. This comes from economy. So we have in time series, we have trend, which is, let's say, typically national income, GDP growth, right? But then we have also seasonality. So let's say that you are in retail business, so you know that in December you have regular seasonal peaks, and then in January the sales goes down substantially, and so on. But then we also have larger cycles, and this is connected with economical cycles when all of the world economy is growing or in some area is growing, and cycles when it goes down. And what's left is noise or errors. So the problem with this data is cycles are very similar to seasonality, just that you typically don't have data. But it's just seasonality on larger time intervals. So depends on what are you trying to achieve. You might to prepare data by removing the trends, so removing maybe the inflation. Or you want to remove the seasonality if you want to get more long-term predictions, forecasts. You want to remove seasonality. And sometimes you need to standardize standpoints. What does it mean? Imagine that you are doing churn detection. You are selling services, so some people are leaving you. And somebody left in July, another one in May, somebody in March. So it's kind of hard to compare this data to find the reason why these people left. So you can standardize time points to have one time point of churn. And then you measure months before churn, and now you have comparable data for all rows. So now you can try to predict. You have also other rows where this is green, so churn didn't happen. So you can try to predict this last time point variable. Is this still my customer or not? Remember multiple linear regression. If we are talking about continuous variables, we have just defined this. We want to express response or target variable y as a linear function of multidimensional input feature vector. Now, if we use, instead of these independent variables x1, x2, and so on, if we use the dependent variable in previous time points. So instead of x1, I use epsilon in time point current minus 1, whatever it is, day, month, year. And instead of x2, y in time point current minus 2 time points. Then I got so-called autoregression. I express dependent variable with previous values of dependent variable. So this is autoregression. Now, remember that with estimation, I could check the quality immediately because I had some results. I can test it, so I can check this immediately. Now I have a problem because I'm forecasting the future. So with linear regression, I'm actually estimating only the mean value. However, I can also estimate standard deviation, a little bit more complex formula, but the same logic. So I can also estimate the standard deviation. And this is useful for forecasting. Why? Well, because when you see that estimated or forecasted standard deviation is growing substantially, you stop trusting these forecasts. They make no sense anymore. And you will see this in a very nice Microsoft time series viewer in a very nice graph.
Now, how do you prepare data for auto-regression trees when you have regular data set like movie sales, drama movies in August, action in August, science fiction in August? So you kind of pivot this, right? So you define last time point as time point 0 for drama, and time point 0 for action, and time point 0 for science fiction. And then, let's say last time point is December, or I don't know, maybe it's even more. And then you define November as time point -1, and October as time point -2. And at this moment, you define all of the variables in time point 0, current, as predictable, and others to calculate to multiple linear regression formula. So what we got again is regression trees. And we got piecemeal multiple linear regression formula. We actually got auto-regression trees with cross-prediction, enhanced auto-regression trees. Remember, auto-regression trees are using values of the same variable in previous time points. So, like here, I use this value to predict this value. And this value from this time point to predict the same value. But we have, remember in the previous slide, we have drama and action and science fiction movie. And these three types of movies, three categories in time point 0 were defined as predictable, but all other were input. So I can use input from time point -1 of drama movies to predict also science fiction movies, something like this. So this is cross prediction. Nice. This is, once I have this multiple linear regression formula, I can use linear interpolation for time points in the future. But we are not done yet. This is one algorithm, auto-regression trees with cross prediction. But we're not done yet. There is another algorithm, so I'll come to another algorithm for forecasting. So I will start with moving averages. You see, moving averages are smoothing the function of a variable in time. And they might be very useful in many cases, because you get rid of these peaks and valleys. You smooth the line, it's easier to see the trend. And for long-term predictions or forecasts, you are interested in trends, not so much in this variability. So we can calculate simple moving averages. There are many different definitions. Simple, like, let's say, last three values divided by 3, or I can use some weights, or I can even use previous moving average, like exponential moving average, in calculations of the current. So exponential moving average in time point I is value in this time point multiplied by some weight plus previous exponential moving average multiplied by some weight. And the sum of all weights must be 1. So I'm smoothing these values. Now let's define some specific ways of calculating these values. So let's define two named operators, lag and difference. So lag operator operates on an element of time to produce the previous element. We could also go the opposite direction, lead, right? And say lag on y in time point t gives me the previous value, lag operator on this. Now we can use more time points from the past, so we get lag exponential, right? A lag polynomial, so we can raise this to arbitrary integer powers. And remember that we also have some noise or error. So we can also express errors as lag polynomials of previous errors. We can have similar definition also for errors, right? Now, what's the difference operator? This is a specific case of lag operator, which simply adds a constant difference to previous value to get the current value. And again, we can get difference polynomials. Why are these operators important? Remember the time series decomposition. Of course, difference operator is directly connected with trend. Lag operator, especially lag on errors, is connected with noise, what's left with errors. But also, depends how many time points we use in the past, lag can be also connected to seasonality and to cycles. And we are just using similar approach as for moving averages. And actually, by the way, exponential moving average is many times used as the simplest forecasting method in economy. Now we have the formula, now you can use it and pretend that next time point is the current. So you use this formula and calculate next time point. So now we have these specific operators. So we express the value as lag polynomial multiplied by some difference polynomial and errors as lag polynomials. So we can define general autoregressive integrated moving average formula. And this is not a single formula, this is a family of formulas. Depends on how many these time points you take for lag operator on values, lag operator on errors, and difference operator on values. And this is general equation. So we express current value, this is polynomial for the values. Is it missing bracket here? Yes. So we have some lag operator, some difference operator, and lag operator on errors. So this is standard way of expressing. It doesn't look very nice. Usually we express polynomials like something equals 0. And now we express like if we calculate all this to get the current value, what's left are errors, is noise. This is how it's expressed. And why do we use this terminology? This was developed by two statisticians, Box and Jenkins, and they use it for the first time, so we still use it. It's so simple. So simple. So now we have a family of algorithms or family of formulas. Some of them even have some names. So ARIMA 001. In every time point, I'm just adding a random error, so it's a random walk. Or ARIMA 110, I'm not taking care about errors, but I'm using one previous time point for difference and one for lag. So it's first order autoregressive model. Constant growth with errors, removing all of the seasonality and cycles, and so on. And then we have multiple ways of expressing this, and not, of course, we have enormous number of combinations and we don't have specific names. Now, of course, the question is, which algorithm is now better, RTXP or ARIMA? Now let's try to present these algorithms and their forecasts graphically. So this green line, this is kind of actual sales. Goes up and stays and goes up and so on. So this is moving average. So this, if we split moving average completely, as much as possible, so let's say if I take all of the time points and divide them by the number of time points, I get simple linear formula, right? Piecewise linear regression, which is done by autoregressive trees, gives me something that is much closer to the actual line. Fine, but this is also better for forecasts. Sometimes, yes. Let's say if I want to forecast in this time point, you see this ARIMA would go more like to the right, while RTXP would go up like the actual line does. However, it's not true always. Take a look if I try to do forecast in this time point. Imagine that this is the current time point. Now I have a problem. RTXP would give me forecasts that go completely way out of the real line. So in general, errors for ARIMA could be higher when you are close to the line, close to the time point. So you are forecasting next time point or 2 time points from now. But then ArtXP, if you go more far in the future, can produce really meaningless results. Completely meaningless. Imagine that at some point the sales go a little bit even in negative direction, and you start forecasting in that time point. It simply means that you can even forecast sales below zero. With ArtXP, this can happen. Right. Also depends on your data preparation and how much data do you use. Imagine that I use simple linear regression. These are mobile phone models, model 1, model 2. If I use data on model level and only recent data, then ArtXP could give me very nice results. If I use more history, then again ArtXP gives me meaningless results. ARIMA on short terms worse results, on long terms maybe better results. So in general, ArtXP is better for short term forecasting, while ARIMA is better for long term forecasting. The correct mixture, remember, depends on data preparation. How much historical data you want to use and how far in the future you want to go with your forecasts. Right? Maybe you can smooth data in advance and then you can use ArtXP more, right? Now, how do you evaluate also these algorithms? We already know one method. You try to forecast also standard deviation. Now, what would this mean? If I go to this, let's say to this graph, I could forecast also standard deviation, right? And draw it as deviation from this forecasted line, and imagine that at some point this would go below the zero. So I know that with this standard deviation it's already completely possible to forecast negative sales, so I will stop forecasting. But also another method is to try to pretend that current time point is already in the future and move back and calculate ArtXP and ARIMA equations for, let's say, 3 time points in the past, and then forecast next 3 time points where you have the results. So if forecasts are close, you kind of can trust the model. Of course, forecasting continuous variables, all kind of planning, budgeting, and so on. So let me show you time series. And again, very, very nice algorithm is in, I will not show all of these algorithms in R. Maybe the best thing is to go directly to analysis services, because we have very, very nice viewers which show you these ARIMA and ArtXP problems and forecasts. So I'm going to data source view, and I will just add a table from AdventureWorks DW. It is actually a view called vTime series. So I will show you what I've got here, explore the data. So I have quantity and amount continuous variables, and my time point is month. I have time index that is actually denoting me calendar year and calendar month, expressed as integer. And then I have data, originally in AdventureWorks data is on product level, like bikes and so on. So here I have data already grouped based on some product categorization. So I have all family of M200 bikes and region. So sales is already grouped. M200 models in Europe, R250 in Pacific. So this is my time series data. All other columns here are just auxiliary columns. I will not use them. Okay. So let me create a new mining structure. And I will use time series. And this is the view. Now I need a key, right? And part of the key is model in region. But I need 2 parts of the key. I definitely need also time key. And later we will see that Wizard will recognize that this one time index denotes time. It's smart enough to recognize it. And I will use amount as input and predictable. That's it. Continuous, you see, model region is part of the key, and time index is also part of the key, which also defines the time. So let's call it TS. Finish, and let's go to mining model parameters. Algorithm parameters. So you see, we have more complex algorithm because it has more parameters. So for example, these two parameters, maximum and minimum series value, is stop forecasting when the forecasted value is above or below this number. This is something that works on ArtXP only. ARIMA will never give you so meaningless forecasts. For auto-regression trees, minimum support to split the tree. Okay. Now these are important parameters. So forecast method. So by default it's mixed, both ArtXP and ARIMA. And then you have also prediction smoothing. When it's mixed in Enterprise Edition only, you can define also how much ArtXP and how much ARIMA to use. So higher number means more ARIMA, lower, more ArtXP, and this again depends on your data, so you have to know your data set very well and your business problem. For testing, periodicity, I know this is monthly data, so periodicity is 12. It repeats on every 12th periodicity hint node. I don't want to auto-detect periodicity, okay? So it's 12. So this is seasonality. Now I could also add, you see this is in curly brackets, so it's a set, it's denoting a set. So it's a set of values, so I could define another value like 48. This would be a cycle if I would have a cycle in my data. So I will inform the algorithm that it's 12. What does it mean? It says it will take, the algorithm will take a couple of previous values from previous time points. Let's say we are in December. So we will take all values from January plus, let's say, 8 previous Decembers. So we oversample December and get more accurate results. Historic model count and gap, I will go with 3 models. This is usually the same number. I will go with 3 models for 3 previous time points to get the historical forecasts. Okay. Let's deploy this. And let's see the results. So let me just show you a couple of values. So we see for M200 amount in Europe and North America, and by default it is showing 5 prediction steps. Let's remove this so we get bigger graph, 6 prediction steps, let's say. So this is showing me predictions, the dashed line for the forecasts for these amounts. Nice view. But the nice is also this, show deviations. Let's focus on one only, and 200 Pacific. Now you can see it goes up and down very quickly, but because the overall sales is much lower than in North America and Europe, we couldn't see this line properly. So now you can also see that the quality of forecasts goes down very quickly because the line should be. So this is a typical example where you should do some smoothing in advance. So you see, this is a cycle. When you get 2 results, you go back to data preparation. And let's see historic predictions. So now I got this line also for historic predictions. Let me hide the deviations. So now I can see how line goes, and it kind of follows the actual line with a time lapse, but it kind of follows it. So might not be that bad. So let's check for some other. So for Europe it looks even better. So no, for North America. For Europe it looks quite nice in history. So maybe you should even, depends on these results, you can even decide to split your dataset into multiple datasets and create separate models. The other viewer here is the tree model. So here you can see for R250 I have 2 splits, and let's show the legend. And these are formulas in this node. So this is multiple linear regression formula, and below is the ARIMA formula used in this node. And if I would change the blend, the mixture of ARIMA and ArtXP, I could even get rid of ARIMA or ArtXP formula in some of the nodes. Okay, time series everybody would like to forecast, but it's not simple. It can help you to create better budgeting, planning. Many times, companies are planning, okay, over the time. So next year you want 10% more, whatever. But okay. And then it's nice, when they are putting pressure on employees. But the plan says 10%. You didn't achieve the plan. Yeah, but who created the plan? Now it's like in the stone or what? Clustering. Actually, clustering, there are multiple algorithms. There are actually multiple groups or clusters of clustering algorithms. So we have partitioning, hierarchical, density-based, and model-based. And I will show you hierarchical, partitioning, and model. In these tools, I don't have density-based. Actually, density-based was a direction like 10 years ago, but didn't give good results with very complex algorithms. So there are not many density-based algorithms around. Model-based is the algorithm I have left for the last algorithm in this presentation. This is sequence clustering. So Microsoft developed first model-based clustering. So let's focus first on hierarchical. These are the oldest clustering methods. So a hierarchical method creates a decomposition of data points. We have 2 possible approaches, agglomerative or divisive. So either you start from bottom and define first 2, the closest time points as initial cluster, then you add third time point and so on. Or you start from the top and say all time points, all data points are in one cluster, and now I'm splitting this to 2 and then more and more. So starting from top or starting from bottom. And of course you need to define what does it mean close. So you calculate distance matrix between objects. And you can use multiple distance measures. The simplest is just pretend that you have multidimensional space. Points, values of data define coordinates of points, so you calculate geometrical distance. When you do this tree, either you build it from top or you start from bottom, you get a full tree called dendrogram. Then this dendrogram is representing perfectly these clusters. And the good thing about these hierarchical methods is that the results are very readable, so you understand clusters immediately. And even more, you can define what is the ideal number of the clusters. Because dendrograms are drawn also not just which data points go together, but in every next step, when the tree grows, the height difference depends on the distance. So you simply find the cutting point where the height difference is the smallest, the biggest. And say I have this number of clusters. How does it work? So I have these cases based on 2 variables. I created a 2-dimensional data space. And you see that B and C are very close, D and D are very close, A is quite far away. So let's start from the bottom. So first we will join B and C and create cluster BC. And then cluster DE. And then next step, you see, and the height difference is very low, F is very close to this cluster DE. Next step, join BC with DEF, and finally we add A. Now we can also see difference in height from step to step. So maybe here the best split would be here. So we would have two clusters, A and everything else, which is clearly the same as here. What's the problem with hierarchical methods? Of course, they are not scalable. They are very useful if you have 40, 50 data points with a couple of millions. They are useless. Too slow, and of course, really you cannot interpret. You know, they say a graph is better than 1,000 words. Yes, if it's limited. But then numbers are better than 1,000 graphs. Real men use numbers, sorry girls. Use numbers, not graphs. So, partitioning methods, k-means. This partitioning method divides dataset in predetermined k number of clusters around the average location of the cluster. So again, we define a record space with attributes as dimensions. And again, values define data points in this hyperspace. Now, we have to assign cases to means, but we don't have means. If we would have clusters, we could calculate means. If we would have means, we could calculate clusters. So it's an endless loop. So we break this loop by simply randomly create these k-means. Okay, can be even some heuristics, use some probabilities, but if our k is 5, we add 5 cases and say these are our means or centroids. So this is our fictitious cases. Now we can assign each actual case to the closest cluster. Again, we can calculate the distance, and now we have clusters. But now when we have clusters, we can calculate these means or centroids. So actually these centroids move. Once the centroids move, we can recalculate cluster membership. And then we continue until some stopping condition. Now very nice is if cases stop jumping from cluster to cluster, then I'm done. Otherwise, it could be just the number of iterations if it goes too far. So how does it look like? We have these data points. These are my initial means, randomly selected, and take a special note on this green case. So initially I calculate cluster membership, and turns out that this case is the closest to this centroid. So I say this case belongs to this middle cluster. But now I have clusters, so I can recalculate the means. And the centroids move. So when I recalculate the clusters, this green case is associated to the bottom left cluster. Now I recalculate the means, recalculate the clusters, and green case doesn't jump from cluster to cluster. So we are there, we are finished. This is so-called hard clustering. K-means is known as hard clustering. So each case belongs to exactly one cluster. Let me expand this sentence even more. Each case belongs to exactly one cluster with 100% probability. I'm still saying the same sentence, just a bit expanded. Now imagine that instead of geometrical distance, I would use some kind of probability function, normal curve, probability function to calculate the probability that this case is in this cluster, right? So we use centroids again, and then we try to cover cases with bell curves on each input variable around this case. So clusters kind of overlap. One case now belongs to all of the clusters. So this is initial state. We have k-means, we create bell curves and try to cover the cases. And then we change the parameters of this Gaussian distribution in such a way in each iteration that we cover more and more points with some probability. Now, every single data point belongs to every cluster with some probability. So this point let's say, belongs to the rightmost cluster with probability 0.9, and to this one with 0.007, and to this one, more you go to the left, the lower probability, 0.000. So this one fits very well in the rightmost cluster. Now take a look at this point. It's quite far away from the means of both clusters from the left and right. So the highest probability is probably for this cluster, but it's still low. It's at least 2 standard deviations away. So it's already 0.04, let's say. And the second is 0.03, and all others are much lower. So the highest probability is still low. What does it mean? It simply means that this case doesn't belong well to any of the clusters. So soft clustering can be used also for anomaly detection. Remember in the first presentation, those who were here, I said you use, for example, decision trees to predict frauds, and then you control it with clustering. So this means finding anomalies without any previous knowledge. Should be worse than decision trees, but if it's close to decision trees, then it means the decision trees model is obsolete. Also, this can be very well used for data cleansing, for advanced data cleansing. So, clustering usage, of course, to understand your customers, any kind of groups of rows. This is grouping rows. Finding outliers, only soft clustering. This is also fraudulent transactions. They can even be used for predictions. If you have a target variable, you calculate clusters without its unsupervised method. You don't use it in calculation, but once you have it, you can calculate the distribution of the target variable in this cluster, and then use cluster membership as input for predictions. Let me show you 2 clusterings, or even 3. Let me go first here to my basic predictive models. I will simply add a clustering model here, using the same data, and later it can be even used for predictions. And algorithm parameters. So clustering method, we have scalable and not scalable, but basically we have k-means and expectation maximization. So we have hard and soft. Default is scalable expectation maximization, and default is also 10 clusters. I will just leave as is. Run it. And while it is running, I will go to R and read data in R. And I already created, I highlighted 1 row too many. This is already creating a distance matrix, geometrical distance. And please note, I'm using modulo 400 on customer key here. Why? Because I'm going to show you hierarchical clustering only on every 400th row. Hierarchical is useful only for a limited set of data. So this is hierarchical clustering. Now let me plot it. So you see this is the dendrogram. Now I can decide where is the biggest difference in height relative. So I can split this in 2 or maybe 3 or 5, 6 clusters. So I can even define with cut3 function these groups, and I can draw a rectangle around this cluster. So now I can see these 6 clusters. 2, 3, 4, 5, 6, yes. Yes. And let me go here and go to mining model viewer and check the clustering model. The problem with these partitioning methods is that I have no clue what these clusters represent. So first I can see that this has more cases because it's darker than this one, right? Now I can also color based, let's say, on gender. Doesn't give anything interesting, maybe number of cars owned. So in cluster 8 I have mostly state 0. Let's see state 4. This is in cluster 7 and 6. I can get very condensed report on distribution here. So these are all input variables in all clusters. So now I can get some labels. So apparently here is education. So we have in cluster 4 or 5, we have graduate degree a lot, right? While in, let's say, cluster 9, we have partial college mostly, and so on. And I can also check characteristics of a single cluster or cluster discrimination, which is similar to discrimination of view in naive. So what makes cluster 6 different from all other clusters? So this is how I can get the understanding of the clusters. And let me go to my initial sheet here and show you in Excel, very nice thing. In this table analyze tool, highlight exceptions. I'm using everything but customer key as input. So what is this doing? It's doing expectation maximization algorithm, sending to analysis services. And then it will also highlight me those cases that do not fit well in other cases. So those are suspicious cases, so the combination of values is suspicious. This is very nice for advanced data quality checks. And you see, this is detecting anomalies. Now it's sending DMX queries to analysis services. So it's even with only 18,000 cases, it already takes some time. This is general report, but let me go back to original table. First row is already highlighted and there are more down. So these are rows that combination of values is suspicious, and this is the most suspicious value. The row that doesn't fit in any other set of rows, clusters of rows. Wow. Association rules, finally a simple algorithm. Market basket analysis, very nice algorithm for market basket analysis. So it's searching, we do find a transaction, like invoice or order, and items on this transaction. And then you search for items that appear frequently together. Now, of course, you can solve this in SQL, like in Transact SQL with some distinct counts, and then it's you can use distinct counts in OLAP cubes, in MDX, and in DAX, and people are doing this. Don't do this. It's much more simple to use association rules algorithm and gives you perfect results, better than you will get with distinct counts, because besides these item sets, it will also give you additional coefficients that are very useful for evaluation. Support is the number of rows of the item set compared to total number of rows. So support for the rule cola and frozen pizza is 0.4. It's 2 out of 5 transactions. Support gives me the absolute evaluation of the rule, right? Now, what about direction? We have combination cola and frozen pizza, but is direction important? So I can express this statement in 2 ways. If customer purchase milk, they will purchase potato chips, or if customers purchase potato chips, they will purchase milk. Now take a look at here. Milk appears in 3 transactions, while potato chips only in 1. So whenever potato chips was in the basket, in all of those cases, milk was also in the basket. The opposite is not true. Only in 1/3 of cases, the potato chips was also there. So we define confidence as support for the combination divided by support for the condition when we express a rule as a if statement. And we see that confidence, we can be much more confident that milk will be in the basket when potato chips is in the basket than if we turn the order. So it also drives you how you put these products on your shelves. And importance, well, basically we are measuring only positive associations here. But what if I have also negative association? What if having an item in a basket lowers the probability of another item? This is what you get with importance. Basically, the idea is simple. You use logarithm, which will give you negative values for negative associations. And the higher negative value, the more chance, the higher probability that an item is not in the basket if another item B, let's say if item A is in the basket. So all of these coefficients are automatically calculated by association rules, and really no need to use any kind of manual thing. So let me go and define association rules. So first of all, I go back to data source view and import tables. Now I need parent and child table. Parent table will define transactions, and child table will define items of these transactions. Okay? And first of all, I can define also logical primary key. I cannot redefine it. Order ID, order number is the logical primary key, so I will have to change this. This wizard didn't give me a correct answer. And logical foreign key. And I cannot change this, it's wrong. But unfortunately, I cannot update this in data source view, so I will have to update this in mining structure. So now let me go here and create a new mining structure. And I will use association rules. And my case table is now orders, and nested table is line items. So I'm not joining it. Analysis services supports nested tables. For R, I would need to join them and then redefine transactions, so more work. So now this is not the key. I'm not using customer key. This is the key. And also model is the key. And model is also input and predictable. So I'm searching models that are there in the same transaction. And that's it. And I will not test this. This is not predictive model. So let's give some short name, AR. And let's go to mining models. And I will just set parameters. I tested this. So minimum probability, this is confidence. I will lower it a bit to get more rules and raise this from 0 to leave it rules that are not important. Let me deploy this. So very simple algorithm, also doesn't need a lot of data preparation. This could be very nice initial point in your data mining life, you know, because if you have, typically sales data is good data, high quality. You must know your customers, you must know their tax ID and so on, and their address. So data is there, not much missing data, and not much data preparation. So let me show only attribute name. So these are rules. So if Turing 1000 is there and water bottle is there, then road bottle cage is there. And probability, what is probability here? Microsoft has problems with naming. This is what I called in the slide confidence with the standard expression for association rules. So this is confidence. Just in Microsoft terms, it's probability. Probability is more general. And this is important. So we have positive correlations. We don't have many negative, but yeah, here it's a very small one, but it's negative. So it would be a bar, red bar, but it's so small that you can't see it. So this is negative correlation. If Sport 100 bike is in the basket, then Mountain 200 will not come in the basket. Here are item sets. So I can see the support for them, and I will say only item sets of size 2, right? 2 or more. So I have 993 cases with mountain bottle cage and water bottle. And let's say here with lower with item sets, 3 items in item set, mountain cage, mountain bottle cage, mountain 200, and probably water bottle is appear this item set in 343 cases. So we are searching by default to item sets up to, that consists from up to 64 items. And finally, this is a very nice viewer, how these things go together. This is extremely nice viewer. So you see, we also get confidence, which gives me the direction. We also Get this, so we have from road tire tube, we have direction to LL road tire. And this is an important rule. If I go back to the top, I can see that this Sport 100 is an extremely important product, so this should be arranged in nearly every package. And then we have this kind of transition product. Cycling Cup has also its local cluster of products, so also very important. So you see, nice viewers, easy to use. Why would you program very complex applications? Last one, sequence clustering. Not so simple, so I will just briefly describe it. So it's a model-based clustering. So it defines, instead of centroids, it defines models and tries to associate cases to models. And how do we define a model? Well, for sequence clustering, Microsoft defined its sequences as the model, sequences of events. So we must have some sequence inside the data, either from time or from any other sequence. So, for example, you can use it for advanced market basket when you also have the sequence of items in the basket. Let's say for web sales. For retail store, you cannot use it because it's completely mixed when you come to the cashier. So we have either simple sequences, like in traffic lights, or complex, where not all states are observable. And we have sequences of higher level, higher degree. Here we have only one previous state that is interesting for the current state. For traffic light, from green goes always to red and so on. So we describe sequences with Markov chains. So describe them with a set of states, and we create matrix of transition probabilities. So transition from this state to this state, probability 0.9. The order of this matrix specify how many n previous states depend on the current state, and of course the size of transition matrix grows exponentially with n. And if some states are hidden, you cannot see them, you just know that they are there, then we have hidden Markov model. So this can become extremely complex. Fortunately, Microsoft sequence clustering uses Markov chains of the first order only, no hidden states. So let's say website usage. From homepage of your company, in more than 50% of cases, people go to blogs. And then when they go to blogs, they go to SQL blogs. And from SQL blogs, they go to BI. And 1/3 of those who read BI blogs go to data mining. Now I can calculate the probability of the complete sequence. And the sequences with the highest probability are my models. And then, after I have this model, then I can assign cases based on probabilities to the closest model, to the closest sequence. So how many sequences are there? Microsoft sequence clustering is very smart. You define number of clusters, and this defines your number of sequences. Like with clustering, we had 10 clusters. However, this is dynamic. This is the minimal number of clusters. Sequence clustering can split a cluster into two if it makes sense. Imagine that the probability, let's say I have 4 clusters. The probability of the sequence in the 3rd place, the whole sequence, is 0.7. The probability for the 4th is 0.6. The probability for the 5th is 0.59, but you declared only 4 clusters. And the probability for the 6th is 0.1. So definitely it would make sense to have 5 clusters. So sequence clustering will split the 4th into 4th and 5th, and you will get 5 clusters. So the algorithm parameter number of clusters is just the minimal number of clusters. How do you use it? Well, sequence clustering was developed with the idea of analyzing website usage. But you can use it for any data with sequence, like for advanced association rules, for web sales. Besides getting the item sets and the rules, you also get the sequence of putting products in the basket. So, for my last demo, I'm creating a new mining structure. I will use the same views, but in a different way. So for sequence clustering, I'm going to use again orders and line items as nested, and again a customer key is not the key. It is order number is the key. But this time, line number is also part of the key, because line number, these are web sales, line number tells me the order. And model is input and predictable. This is different. And you see, I also have, like I had key time, I also need key sequence, something that is sequential for sequence clustering. I'm not doing any tests, so I will call this as SC, finish. Show you quickly the algorithm parameters. So basically cluster count defaults to 10, and I will get at least 10 clusters. So let's deploy this. Okay, and let's see what we got. So, come on. First of all, you can see immediately that I have more than 10 clusters. It's cluster 13 here, right? And now I can check what's inside these clusters. I get even more complex cluster profiles, very condensed view. Fortunately, I can expand it a bit with Mining Legend. So these are item sets combinations here, and these are probabilities for the most important items here. Again, cluster characteristics, cluster discrimination. These are sequences, you see, start. So this, we have some starting and we have some ending clusters as well, and some clusters in between. Again, you can find what favors one cluster compared to all others, but this is the nicest view, state transition. And you can find state transitions for any cluster, for example, for cluster 4. Let's see state transitions, and let's say links. So you see, here I have direction, I have probability and everything. So starting with mountain 400W, the probability is 78% to go to mountain tire. And then the probability is 58% to go to mountain tire tube. And apparently the other probabilities from here are lower. And you see in this cluster, from Sport 100, you also have remember, Sport 100 was very important product, but also look at the probability. This was edit state by sequence clustering, end of sequence. So take care not to put Sport 100 in the beginning of the chain. Put it in the end, right? And it will go very well with all other products. But if you put it in beginning, it will finish the sequence. So in this case, sequence clustering gave me advanced association rules. Okay, I think it's enough. I mean, and remember, I just introduced the most popular algorithms. Of course, in R you have dozens more. Some specific might be useful for some specific tasks, but these are, in these two models, the most popular and important ones. So any questions before we take a lunch? Don't want me to start over? Maybe you didn't understand something? Okay, thank you very much and enjoy the rest of the conference. Discrete variables. So now I will create a new named query which will add age and yearly income to continuous variables to my data. So let's call it target or just TM regression. So I will use this for regression, copy the query and define the key. So what I got now is I got a couple of continuous and couple of discrete variables. So I have to create new mining structure because I'm not sharing the same structure. I'm having different variables. And you see, there is no regression trees algorithm. Actually, regression trees is hidden in decision trees. It's there, so I will use decision trees, and I will feed decision trees also with continuous, predictable and input variables. So TM regression is my case table. Now let me define inputs and predictable. So I will use this one, let's say like yearly income, okay? And then I will use also, I will pretend number of cars owned is something between 0 and 4. I will pretend that this is also a continuous, so I will have multiple linear regression formula. And definite, no, this is input, and definitely age is input. And I can use all of others, even bike buyer, commute distance as inputs. I didn't define which one is continuous yet. Let's see here. The wizard properly found that age is continuous, bike buyer is not, it has only values 0 and 1, so it is discrete. I will leave number of cars owned as continuous, although it has only 5 different states, and yearly income. So I have 3 continuous variables: yearly income, number of cars owned, and age. I will not use the testing, although I could use similar testing, not leaf chart, it's not so simple, but you can still test the values, okay, and measure the total deviation. So I will say TM regression, let's call it TM regression trees. Finish.
Not all of you were on the first part, so just a brief introduction. I'm dealing with data mining and SQL Server for 30 years, wrote 13 books and coming to 10 courses and more. And I'm focusing mostly on these topics like data mining, statistics, advanced data modeling, data quality. So in the second part, I'm going to describe estimation algorithms, linear regression and regression tree. One more kind of a predictive or classification algorithm support vector machines. Time series, different clustering algorithms, association rules and sequence clustering. So a lot of work to do, but I assume that either you visited the part 1 or are already familiar with definition of data mining, so I'm skipping the introduction, which took me like 1/3 of presentation in the first part, so we can focus directly on algorithms. So remember, the focus is on algorithms. I will show demos in analysis services, in Excel and in R, but the focus is on algorithms, not on tools. So the idea is to explain how these algorithms work, how they get data, the results from the data, and so on. So let's start with estimation algorithms, and those who visited the first part remember the main difference, or the difference between predictive and estimation algorithms is that you predictive or classification algorithms work on a discrete target variable. Now we have a continuous target variable. And of course, if you want to express one continuous target variable as a function of another continuous variable, it means you need at least 2 continuous variables. Otherwise, linear regression makes no sense. It will return you the result in the form of a constant. So y equals a constant. So in linear regression, we want to show one variable as a linear function of another, like y equals a plus b multiplied by x. So in multiple linear regression, we have more than one independent variable or multidimensional feature vector that consists of these multiple independent variables. So y equals a plus b1 multiplied by x1 plus b2 multiplied by x2 and so on. So logistic regression is basically a very simple neural network with no hidden layers.
Similarly, we can define linear regression is a very simple regression tree with no splits. One formula for the global data set, and you get linear regression. So regression trees, I have similar points as with linear regression, just that I split this based on some input variable into subsets, and then I calculate the multiple linear regression formula for all of the subsets. Now I can estimate this target variable on new data, use discrete variables to define the subset, and then use the formula for the subset to estimate the outcome of the continuous variable, right? Like family income for a credit applicant. So, as I said, in order to get something meaningful, we need at least two continuous variables, one predictable and one input. Linear regression is extremely simple to understand, maybe even overused algorithm for all kind of forecasts. Definitely overused because, you know, we are prone, as human beings, as people, we are prone to use it because we live in linear time. Time changes linearly, so we understand linearity very well, but non-linear functions, we don't understand them. You know, they are not built in, you know, in us, so we don't really comprehend them. So we tend to simplify problems to linear problems. And then, of course, you make big mistakes if a problem is not linear. Regression trees might be much more accurate in many cases, because even if the actual functional dependency is non-linear, like something like this, if you get this piecemeal regression tree, you can kind of follow the curve very, very nicely, and still is easy to understand. So it might be very, very useful. Linear regression is also useful, but as I said, maybe even abused and overused for many cases where a more complex algorithm would be more appropriate. So let me go to my Visual Studio and let me define a new named query in my data source view. Remember that for the first part, I used only start with one dependent and one independent variable. So these two variables form a two-dimensional plane, and the values define coordinates of the points in this plane. Now, if you draw these points in a scatter plot, with linear regression, you are searching for a line that best fits all of the points. So this is what you are searching for. So how do you define the best fit? So the points must be all together the closest to the line. So this is best fit. So you measure the deviations from the line, the difference between the actual value for some point from the line value, okay? From the line value. You want to minimize these deviations. Now you cannot just sum them, because some points will be above the line and some points will be below the line. And if you use simple sum, then this will not give you any information, because most of these values will annihilate each other, so the sum will be 0. So you will not find the best fit line. So how do you overcome this? You square the deviations, so you are measuring squared deviations, right? And then you can calculate the slope of the line and the intercept of the line with the y-axis. So the slope, you calculate deviations from each point to the mean of this line, y, and multiply by deviation of x in this point from the mean of x, divided by the sum of x minus, in this point, minus mean of the independent variable squared. So intercept is then calculated with help of slope, is the mean value of y minus slope of y multiplied by the mean value of x. And this is the formula. So how does it look graphically? So you have these points in a two-dimensional plane, and what you try to do, you search for the line that minimizes these squares of these deviations. Now this is very simple, and then you use this line with linear interpolation, you predict new values. Okay? So you simply extend this line and predict new values. Now this might be oversimplified model for many business cases. So this is also a global model. So we have a single line that covers all data points. Now not all or most of business relationships are not that simple. So if you remember, neural networks and even logistic regression try to do some nonlinear transformation. Now with these nonlinear transformations, we have another problem that is hard to understand the results. So regression trees go to a different direction. So we have trees, so it will be something similar to a decision tree. So we subdivide this working space, this area where we define this multiple linear regression formula. So we divide these points in subsets. And then we calculate multiple linear regression formula for each subset separately. So we got piecemeal multiple linear regression formula. So how do you define these partitions? Well, you can use discrete input variables for this division. And then you can continue to divide these partitions more and more until again some stopping condition. And this is of course completely, the first part is completely the decision trees algorithm. And once you have all of the nodes you need, then you can calculate multiple linear regression formula in each node separately. So you got piecemeal regression formula. And regression trees can be even smarter. Now imagine that you don't have any discrete input variable, but you have multiple continuous ones. Regression trees can be smarter. You can define these splitting points also in the points of nonlinearity of these continuous variables. Imagine that you have some variable that goes like in sinus. So in every peak or valley you define a cutting point, splitting point, and then you use this variable as a discrete one for splitting the tree. And the rest ones that do not have any points of nonlinearity are used for regressors, for multiple linear regression formula in these nodes. So remember from the first module, or first part of this data mining algorithms, we said that